Okay, welcome to Advanced Fluid Dynamics at Portland State University. It's ME 541 is the class you should be signed up for, or 641 if you're a PhD student. I'm your instructor, Samuel Moeller. Here's my email for questions. Hopefully you've already gotten an email from me on this class, and you've taken time to peruse the class website I made. It's a Google site, so it looks pretty good. I think it's user-friendly. It looks good on your phone, too, so anywhere, if you have questions, you can kind of see what's going on in the class. It's basically the syllabus, but I'm going to go over some of the points right now. If there are questions left over, please contact me for questions, and mainly right on our Slack channel. Now, you'll have an invite to get to that Slack channel on the website itself. You just go to the Slack thing and click the invite link. It should direct you right to that Slack environment. If you don't know what Slack is, you can click the link, and it will direct you right to it. It's just basically a big forum so that you can talk freely, post questions, answer questions, and it makes learning a very vibrant experience, especially during this remote times. I've taught it with classes before, and students just blow up with questions and do amazing things. They learn pretty wonderful things. Sorry. I have a mic I'm recording on as well, so hopefully the audio is good for these lectures as well. So kind of classic things right there. Another thing everyone wants to know about is how do we do the grading in the course? Well, the grading in the course is 50% homework. There are 6 homeworks, all ranging in difficulty levels, and I've put a little star rating on how difficult I think they are, but might be different for everyone else. Then there's an exam. This is multiple choice, actually. Right, multiple choice exam. So just really concept questions we're going to talk about in the exam. Really, if you've done really well in the homework and you've understood what the homework's saying, internalized the solution, can interpret the math statements that are in it, that's great. And then you're just going to apply those to the final exam. They're multiple choice. You're really saying, like, that term's bigger than that one, et cetera. So really getting at the heart of the intuitive concepts fluids teaches you if you look at the solutions. And then 25% of that, which is half as important, right, as homework, because this is a really big thing, is the paper that we're going to do in the class. So this is really a simulation or like a high-fidelity, sort of a high-fidelity, safe run of trying to write papers. So maybe you've never done something like that before. Maybe you are currently in a lab and you are writing papers, but if you haven't gone through that process, I think it's always better to practice more and more. So we're going to be doing like a sort of a 10-week run to try to create a scientific article. And if it's good enough, let's go for it. Let's publish it if it's really good. And then 10% is actually Slack. Now, I put 10% on the Slack because in other classes I've taught, all the students that are very active on the Slack channel do really well. And also, it's an incentive for you, even in the remote world of education, to not like slack off and to not just sort of like not participate, right? So I mean, 10% of a grade is you just being on Slack, asking questions, answering questions, and participating that way. We don't have a classroom, so I can't ask you questions all the time, or you can't ask me questions directly. But if you ever do have a question, I really hope you post it on Slack and don't just personally email me, because then everyone learns more from that. And if you have a personal thing, or maybe it's a weird, just you don't want it to be public, then you can just direct message me on Slack. And right, I mean, I have Slack on my phone, so I'm very, very, very quick to respond if you use the Slack platform. So that's the grading. And then the textbooks that we have for this class. Now, I post my lectures freely, and then I also post the notes I use prior to making the lecture. So you'll have those 2 avenues to try to learn this stuff or help you when trying to solve these homework problems. But then there's these textbooks. They're not required, but you can certainly, if you want to, I think every good research fluid person should have some library of good texts, I think, digitally or in physical world. So there's Pantone Incompressible Flow. People are kind of split, I think, on this one. Some people hate it, some people love it. Students don't like it at first, but then you grow to appreciate it, I think. There's White Viscous Fluid Flow. This is just a fantastic book, and everyone usually has the copy of it. And then I use Lifshitz and Landau Fluid Mechanics. This is part of like a 7-series, 7-volume sequence of physics that these guys wrote. And this has many awesome like solved example problems in it, actually. Just crazy solutions. I like Childress Theoretical Fluid Mechanics. I don't remember where I found this book. I just like it for some things it goes over. I wouldn't recommend that one. Certainly you can look at it. You might not. I think it's just the good words and good like handling of the math, I think. I like how it's put out. And this is a silent sleeper hit, I think, of fluids. It's a I don't know how to say his last name, but Elementary Fluid Dynamics is a great one. Little tiny book, but wording's great, very intuitive language to describe the solutions and techniques. So those are the 5 that I'll be using, translating to you, and hopefully maybe more, maybe putting some spin and helping you learn how to do these fluid dynamics problems. Okay, so those are sort of the mechanics of the course, or just little things you should help to know. And there's a couple more things I need everyone to do. So in this class as well, you will need to learn how to use software, right, or some numeric solvers, right, or really numerical. Right, you need to have some sort of way to quickly solve some sort of nonlinear ODE, right? So you can pick however you want to do that, but I can only understand so much, so I do restrict you to either doing this with MATLAB. They have great ways to solve ODEs and even PDEs with this software. You can use Python, right? A lot of packages do great jobs of solving ODEs. What else am I okay with? I mean, you could even do Excel, right? You can if you know how to do like a 4th order numerical solution, right? You can just drag and drop to a solution and produce a plot. Really, you need this to produce plots of solutions so that you can see what's going on, okay? And one other one is the Julia language. It's kind of like another type of Python. It's new. I think it's at 1.5 now. Release. I mean, well, Python's, I think, 3.2. So this is a brand new one. It's really fast and just an up-and-coming scientific computing language. If you want to take this time for this class to learn how to use that to solve ODEs and do math, go for it, right? It'll be awesome. And then the other one the other one being Mathematica. Right, Mathematica is also a programming language. It's also or Wolfram, right? So you've done Wolfram Alpha before. That's called Mathematica. I recommend this one. I mean, these ones are pretty quick, I think, if you haven't done any numeric stuff for solving an ODE numerically before. Those two, I think, are maybe kind of the easiest to first use, right? These you have to do programming in Excel. It's just a giant file, kind of not worth it. Okay, so if you're at Portland State University, you can VPN and get your MATLAB license that way. It should be on all the computers, but since we're remote, that might be difficult. Obviously, Python's free. Hopefully, you have Excel. This is also free. And then this one you can get, right? If you go right, Wolfram, right? It's on the cloud, so just through your browser, your internet browser, you can use Mathematica and learn that syntax. This is a really good one, though. I definitely use it a lot for any sort of like analytical math stuff or just calculations, because it's a symbolic solver. So I recommend going on this website and making a basic free account, right? Just sign up for right? It's just free, and it's just free, and then through your web browser, you will be able to solve these ODEs. And what I mean by that is like, right, you'll get to like some horribly nonlinear ODE. So here's an example I have. So, right, if I gave you something like that, f dot dot. Let me just get my note here. So here's the right. If I gave you this ODE, ordinary differential equation, right, and I said plot some solutions of it with boundary conditions, you should be able to do that rapidly and fast. And Mathematica is good for that. So that is my recommendation, and MATLAB does it too. But just being quickly able to find solutions to nonlinear ODEs helps, because then you can tweak parameters and get a sense of what's happening. Besides the ODE solver, I also highly recommend learning or using Desmos in this class. It's also just on your browser, and it's just a nice graphing calculator. It won't solve an ODE for you, but just for quick plotting. right? For quick plotting, right, seeing I use this a lot for this. Right, just if you have an expression, just plot it real quick to see is it negative or positive always, or other types of quick questions like that. Desmos is fantastic for that. It's a lot faster than trying to plot it in MATLAB or Python or anything else. You just go on your browser, type the expression, and then it just quickly pulls it up. Again, can't solve the ODEs, but those are some great tools for the math in this class that you will need to use, and I highly recommend right now setting up that Mathematica account that's free and just looking at the help bar and documentation. I will also quick say for the cloud, so for Mathematica, just look at the documentation and get really good at using the functions plot, NDSolve, and DSolve. Those really are the three. And then I also would highly recommend looking at documentation for manipulate. This is a fantastic function this language offers that you can tweak parameters and quickly see what the curve does. So if you're up to date on those four, then things will go a lot quicker in the class for you. So make the account, look at the documentation or help page for each of these functions. You're a graduate student, you should be able to figure it out and just kind of get up and running with that, right? They have great examples of how to solve ODEs in there as well. So those are the math tools. Now for that paper we're going to write, we'll also need some tools. I'm making the paper, you have to write it in LaTeX, okay? Maybe you've never written in LaTeX before, maybe you have seen it before, maybe it's new to you, but you should be exposed to it at least once to just see how it is done. Because some people only accept a text document for their articles. So if you haven't done it before, might as well get that work out of the way now in this class and see how it's done. So how you write in LaTeX, you can do it any way you want, but I recommend overleaf. Okay, overleaf.com, right? It's on your browser. So through the web, you type in overleaf, and then you start a document, and it has all these great templates, and you just start editing it in your browser, right? It even makes the code, so you don't have to download the tech source code at all. It's just all through the internet, and it's really easy and it's a nice, intuitive way to make the documents. There's even, when you're typing, I recommend looking at the rich text editor, because then you don't have to look at the source code. It won't look like a programming language when you're writing the document, so that can help as well. So Overleaf also has great help and documentation. It also has great templates. Right? And I provided a template on the website, so for this paper, you essentially have to fill in the template perfectly. But doing that process of writing to a template is also a skill that you should learn from this class. So there's two avenues. You're going to learn a bunch of fluid mechanics math, and you're going to learn a bunch of scientific, bureaucratic kind of the, utter guts of science of having to write to a template. So if you're lost in Overleaf, Slack. If you just totally can't seem to do it, then post your specific question on Slack, and then I or someone else that writes in LaTeX can quickly give you the piece of code even to put in there, or how to answer your problem right then and there. So it may seem like a lot right now, but really you're just writing a paper and you just write you just write text and content, and then LaTeX just formats it for you. And just do it through Overleaf. You could download the text. You could download the text source package or text source passage, and then download an editor that you like to use, and do it that way if you're that good. I don't really care how you do it, but it has to be a text document. You'll also be doing the paper. It's a group project, so I'm going to split the class in half, and then you will all select roles for the paper that you want to do, and then get going on it. And it's something that you should start week 1, right? Start thinking about it right now in the back of your head. But don't put all of your brain space into it, right? You can just chip away at it for 10 weeks. No giant hurdles or quick. Just get started thinking about it right now, okay? And if even the first homework assignment is talking about planning it out. So the first homework assignment is making a plan for the term, and then whoever in your group decides to be the manager or the principal investigator role that I assign and talk on the class, then they have to make a plan as well. So each group will receive an email from me saying, like, you're in this group, enjoy. So as soon as you get that email, talk amongst yourselves and pick roles. Immediately. So you're going to get your group assignments, and then I want you to immediately begin thinking about which roles you want to play for your team on this paper. So what are the roles? I'll go over the roles as well, and then we can finally get to maybe some more fluid soapbox stuff. So again, that's just paper. Do it in LaTeX. I recommend going on Overleaf. When you're on Overleaf, use the rich text editor. Makes it easy. Really use the help button. Look at templates. Look what other people do on tech. And then once you get the email, pick your roles. So the roles are going to be, I have one role being the PI. You can only have one PI. You can be a historian. You could be an analyst. You could be an artist. You can be an editor. Okay, so each of these roles, the PI, right, you will be responsible in this paper for most of the planning. Right, most of the planning. Shared editing with an editor, basically. What else are you going to do? Sort of big picture. Big picture person, you come up with a problem usually. And sort of just the all-around person that's making it happen, right? If someone's slacking off in your team, if someone is not doing their part, you as a PI, that would be on you to whip them into shape, I would think. And your grade would be lower, right? As a principal investigator, your grade's going to be based on the lowest of your team, right? So you're taking on the challenge. You might not have to do a bunch of the analytical work or any of that stuff, but you do have the challenge of making sure everyone's doing their best and is on course and track with this stuff. So an historian, if you're doing the historian, you're going to do the lit review, right? So you're going to actually go through and look at the papers and try to solve your problem just through written materials, right? So you probably should write the lit review section. Every one of these teams has to write something in the paper. So historian, right, I've kind of done it where you focus in on doing the lit review and answering questions through other people's works and papers, and then you write a good history and lit review section, basically getting you up to speed if you're reading this paper on the theory itself. Most articles get rejected at first because it's pretty clear that the author doesn't have a good understanding of like the bulk of the theory, and that's because they did a poor lit review. They kind of went their own way the whole time. So this is a good skill. As a historian, you do it, but also, right, you have to tell your whole team about it. So I highly recommend read the abstracts first and then download it if you want to go further. Don't make a giant folder of papers that you're not going to read. And if you're a lit review person, you're going to have to learn how to use BibTeX, right? And again, makes it super easy in the Overleaf. If you have a template, it will already have a BibTeX file. And then, right, you also have a chance to learn like to use like Zotero is a good website. Even Google Scholar outputs bib files or bib entries. So, but as a historian, that's really on you. You take this term to go through a lit review and learn how to use Zotero, BibTeX, and understanding bib entries. And as well doing, right, and as well like going through the process of like digging through a bunch of papers and trying to solve your problem. Analysts, right, so what the analysts are doing, that's kind of like, well, you're doing really well in this class and you're really good at the math stuff of all this stuff, so that's sort of your job. So I would say math, coding, data. One of the biggest mistakes analysts do is they kind of do some math, they kind of do some coding, but they don't generate numbers, data, or they don't have a way to actually generate numbers or data. And that's you being a bad analyst, right? So you can go ahead and talk about doing a bunch of math and coding, but as analysts, you really have to at the end, this is what you have to end up outputting, actual numbers and data. Why do you want those? So that if you're an artist, right, the artist being plots. Now they have the way of making the data, but I'm saying there's just a whole process of making figures. Or diagrams for the paper, right? So someone totally, and this is just such an attention to detail thing that you should learn about quickly. So I just make it its own role. So you're on the line for like telling the story of all the math that you've been doing in graphs, right? So that's on you. And then an editor, you're really good, sort of like the Latex expert, right? You're the one that can really help compile and make the whole paper one thing. You're going to receive writings from you're the one who's going to receive writings from your historian, receive some blurbs from the analyst, receive some blurbs from the artist, etc. Like, for instance, these people should probably spend a lot of time writing really good captions or descriptions of plots and figures. These people should really spend time writing really good methods and analysis sections in the paper. Again, a historian should write a really good lit review, right? And then it comes to you maybe, and you can compile it and really make the template work together, right? And I describe more of this on the website, but right, you're the one that can really compile everything into one single document and also edit their words, right? There's typos, just let them focus on the content and anything else. But then it can come to you, and you get to pass over it, and you can rewrite it, make it a better story. And then even the PI is going to be doing the same thing. So they can generate a bunch of terrible words and horribly written prose, and then the editor and the PI can go over that horribly written prose and make it a little bit better, and then you just iterate over and over and over again. So that's the paper. If there's more questions about that weird way of how I've done group work, again, use Slack. Post it on Slack. And then other people can go, I'm also confused with that. So please. OK, so that was the paper. The exam is just multiple choice. I don't want to go over that, waste of time. So now let's go over this course. OK, how am I doing on time? A little over. OK, so in this course, now let's begin the soapbox. Let's begin the me saying why fluids is the best thing ever. Notoriously, we have to do this, right? If you're teaching a class, you have to say why fluids is the best thing ever. Okay, it doesn't matter, right? So we're going to learn about fluid mechanics, right? So fluid mechanics, right, is a subset of continuum mechanics, right? Splits into two sections, right? Solid mechanics, and then fluid mechanics, right? And this separation is not, this separation isn't pretty clear as to why, I would say. Most people don't understand what the difference is. But right, in this class, right, one thing we'll learn in lecture 2, right, is what really separates these two things, it being a solid or it being a fluid. And it ends up that fluid can't support a shearing force. That's one of the biggest differences of it. And I'll go over that over and over again. Well, a solid can support a shear and can, right, so a solid can exist it can exist in a force equilibrium with a shearing force, unlike what a fluid can do. So later on, you'll even know a more specific separation of what these two things are talking about. And that is, in a solid, you have to talk about a strain tensor and then for fluids, you have to talk about a strain rate tensor. But that's lecture 2. I'm just saying there's a divide of the continuum mechanics. And we focus, right, on this side. So don't worry at all about solid mechanics stuff. screw it. Okay? So we're in fluid mechanics now, part of continuum mechanics, and then there are a bunch of subtopics within fluid mechanics, right? And they're all kinds of stuff. So before, you probably did, in your undergrad course, you did a lot of hydrostatics problems where there's no motion, it's just the pressures in the water. You probably did a ton of Bernoulli's analysis, which is just an energy balance. So in your pipe flow problems and everything else, you're really balancing energy from state A to state B. I mean, what other topics did you probably go over? Or basic transport. Right? And maybe some. Non-dimensional groups, right? You clearly learn about the Reynolds number. You clearly learn about maybe like the Buckingham pi or pi groups, but that's sort of just, that's why it's introductory, right? So I'd say undergrad. Okay, this is the advanced version. So in the advanced version, we'll break it into like very specific topics, right? And that is all kinds of things that you can be exposed to, right? So there is just viscous, right? We have viscous flow. Right, compressible flow. And all these things have very specific meanings in the advanced section, right? Right, we can learn about non-Newtonian flow, non-Newtonian fluid flow. Could do turbulent flow or shear free. There's even subsections of what that is, right? Multiphase flow. Numerical solutions. Sort of surface tension flow. Even heat transfer has a lot of topics that talk, right? Even the topic of heat transfer is really also part of this advanced fluid topics where you talk about the transfer of heat energy, et cetera, right? So there's tons of advanced topics that we'll talk about. Mostly this one, a lot. I have like some stuff on the compressible stuff, right? Not that much. I won't do any turbulent stuff actually because there's another course that talks about that. So I'm just on the hook for these topics. No multi-phase, right? Numerical, yes. Yes on the surface tension. And then again, from this viscous flow, there's a bunch of other concepts as well. Oh, how could I forget, right? There's even the boundary layer. Right? The boundary layer is a big topic as well that you learn in advanced topics, right? Maybe you saw some of it in your undergrad, but here we're actually, right, derive and understand what the meaning of this boundary layer is, where it comes from these Navier-Stokes equations, right? And the biggest thing is all of these, every single one of these topics comes from, right? It comes from right? It comes from a simplification or analysis done on these things called the Navier-Stokes equations, which is the whole topic of the next lecture and the one after that, is really going into exactly how we get these equations, where they come from, and where the assumptions mean on them. Because when you tweak these assumptions a little bit, when you do things to like each little type of term in there, you then generate a whole field of fluid analysis. I mean, the boundary layer, for instance, is a classic example of you go from the full equations, you make some reasonable statements about the boundary condition and about like the speed of the flow, and you derive a new set of equations that govern the boundary layer. I mean, really, the Navier-Stokes equations, you just make right? You just say it's your viscosity is not negligible, and you just have to deal with that term, and you get this viscous flow. Sometimes this also could be, right, there's even one called Stokes flow. But again, you're going to go from here, and you make a really general assumption or a very general statement, and it breaks down to here. I mean, compressible is just saying that the density changes throughout where you're flowing. Essentially, you keep a term that is originally in these. Turbulent flow is just wild. Multi-phase flow, you actually would have like sets of Navier-Stokes equations, right? Numerically solving these things, this beast is a whole field, right? I mean, CFD just comes from looking at this big equation, which we don't know yet, but we'll go over, right? We look at that genetic equation, we just say, how can I make the computer accurately solve it? And just from that, you can get a PhD in answering that, because it's a hard problem as well. Surface tension is the long-forgotten stepchild, I think, of this, because we normally don't think about, right, the tension of the surface forces that happen on a fluid. It's usually a pressure-driven flow, etc. So, but again, you would go here, you would claim also a boundary condition analysis going blah, 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 it has a contact angle, etc. There's a surface tension flow, and then you would derive, or really interfacial flows. So that's sort of the amazing thing about this, right, this idea is I hope I can instill throughout all this term this process of you go from here, you generate a whole field, and then from here you'll just, right, you'll have a couple solutions to look for. And it's, right, that's sort of the main point of the whole class I'm trying to get at, is showing you how you go from this extremely general equation. I mean, this is F equals ma for continuum fluids, essentially, right? And then you make physical arguments to subdivide, and then from there you try to get some equations. And really, I mean, all of these things you learn in undergrad from hydrostatics or Bernoulli's equation, the basic transport laws, and the non-dimensionalization, they come from that process. And then we just feed the undergrads the result at the end of it. Right? And a gigantic trick of going from this way to this way is going non-dimensional. Right? If you don't do this, it's really hard to accurately make some sort of like scaling limit or something, or say that something is small or say that something is big. If you don't go non-dimensional, you won't be able to do that. I mean, you certainly could just guess, and you could have a better guess about it. But when you start off doing this stuff, it's super important to go non-dimensional in all your variables and then look at the parameters and say, aha, that's a small term because I measured it and it's small. So you will do a lot of that in this class. And I hope you learn to like love it and just, I mean, after you do enough scaling and non-dimensionalization, it's almost comical how well it works. Okay? So how do you go from, how do you go from here, and then really you're looking for, you're looking for solutions this way. So you go from Navier-Stokes. So how do you, what's one way to get your solutions or fluid flow? You don't even know, I haven't even introduced to you what a solution is or what you're looking for when you solve these problems. But, so on the website I go over sort of like an algorithm. Now there's no algorithm that's true for every type of problem to solve. That's ridiculous to think there are. There's an infinite number of ways to solve a problem, and there are an infinite number of problems, so it's like infinity to the infinity of ways to solve a problem probably, right? But I just have on the website, I think that there are just sort of, 5 key steps, to your fluid problem. Really homework or just sort of, maybe just fluid analysis, right? So you go from here, and the point, so the first step is you have to have, a well-posed problem, or well-defined. So you have some phenomena that you just maybe observed or you thought about, or it's like, why is my coffee doing that? Or like, why does river do that? Why is that liquid doing that thing? Or why is this gas doing that one thing? That's some phenomena you observe, and then you have to turn that phenomena you observed into some mathematically well-defined problem. And that's incredibly difficult, I think. That's the hardest part. And in fact, with textbooks and homework, this step is already given to you, You look in your textbooks and you see, if the thing is this, and it's exactly this amount of pressure, and let's assume it's like this. So they did this step for you. And even in this class, that will be given to you for homeworks and everything else. Maybe not as much as an undergrad, but even still, this is partially done for you. Why? Because this is the most difficult thing, You spend years doing this process of observing phenomena, and then go, how can I make that a well-posed problem? Okay. Then for part 2, some people don't do this. I think it's super important that once you have that well-posed problem, then you can start making a flow schematic, right? Flow schematics, diagrams, arrows, you know. You go from that well-posed problem and you draw some sort of simplified, idealized model, or the Platonic world, or whatever some people call it. And then you get to drawing a picture about it. And this is important, very important. I at least stress it so much because even though you have a well-posed problem and a bunch of math terms, if you can draw it and write down exactly what each term means, at least in some diagram or picture, you can do more solving in your head because you can just look at the geometry of the problem and you can go, well, that's probably going to shake out that way. But if you don't do this step, I think you know, at least it's a good training exercise. I certainly have met people that are great fluid dynamics people, and they can skip almost all these things. They just do it right off the bat in their head. But that takes a long time to achieve and do. Right? Okay, so then after you have that, you have your picture. Your picture, truly, you haven't made any assumptions on it. You know that it's just governed by the Navier-Stokes equations because it's a fluid existing in some type of space under some type of flow. So you've drawn the picture. You just say, I know only this is governed by Navier-Stokes. All terms, keeping all of them, right? And then you do this simplification. Navier-Stokes equations, right? So, and this is like even coordinates, simplify the coordinates, the x momentum, the y momentum, right? Simplify as many terms as you can from your picture. And this is the step of non-dimensionalization. Or the way I think of it is something called scaling, right? That's this step. And that's important because then you go from a phenomena to a physical phenomena drawn with math behind it, and then you go for this step where now you went from a physical phenomena to a well-posed math problem, but then you actually make it just a math problem by taking the dimensions away from it, right? So then, right, once you do this and remove any dimensions from it, you're just now in math world, right? You're only speaking of just integers. They have no units to them. So all those integrals that you solved maybe in calculus or just weird type of things you calculated in a math course, they actually apply because you now are just like, you know, it's just like something's equal to 1 and only 1, no dimension to it. And then also the benefit of doing the simplification is once you do non-dimensionalize, then you immediately see parameters that kill off terms in the full equation. And then you'll just have a simpler math problem, right? So then when you get to there, you'll have to solve your math problem. Now that's a loaded question, I think, because not all math problems are solvable, right? Right. So that's this whole world of like approximate solutions or some analysis or a numerical solution. An analytical solution is very rare, but if you can get one, sure. Or is it an asymptotic solution, a series solution? You know, even just like a stability analysis. You have your math problem and you just get some answer from it, and it's just math and you redimensionalize. So then after you have some solution, right, then interpret the solution. And this is sort of really kind of a redimensionalize the problem sometimes can help you with this, right? But then after you have you just turn your solution and then you can kind of look at what does this imply to the physics of the phenomena, where it doesn't explain anything about what I saw at the first step. Right? Does my solution actually unveil what's happening in the flow, and I can see it in a term in the equation, or I can see it in the plot that I've made of my solution? Does it answer those questions? That's sort of this interpretation step. And I think redimensionalizing your solutions helps you with that. Some people don't have to do that. They can just look at the terms. But sometimes I think it's nice to go back into the dimensional world. And then 6, I would say, is write it, right? Because I know it's just homework, et cetera, but like that whole point of writing out your homework is an important step because you did all this work where you might as well let people know exactly how you found your, right? You might as well let people know why you now know the coffee cup in the river thing is doing the thingy thing. But writing it's very important, so hopefully in this class you struggle through that idea of really untangling this web in your head that you made yourself from doing that analysis, right? Right. This is also one of the hardest steps. And I think it's different on the website because I have a different algorithm on the website, but I wanted to include the write it. Now, if you're really, really good, actually, I would say you kind of would go from here, maybe just here. Some of the best fluid dynamicist people, they can almost just like skip these steps. But you're going to get there, right? Because you kind of keep doing it and keep doing it and keep doing it, where you can just like look at a phenomena, kind of figure exactly how you could make it well posed within the context. Then you'd already kill terms off, and you already go like, well, if it's like that, it's kind of like this solution. Then you kind of understand it that way, and then you'd almost jump to writing it. Usually what happens is the PI comes up with this, and then they make their grad students do these very hard steps right here. Because they did it a bunch, so now it's their turn, right? They paid their penance. Okay, so that's my algorithms for the class. Right? Nothing is set in stone, though, right? Nothing's perfect. That's just something I have noticed over and over and over again from people that do really well at this stuff. Okay, next, let's talk about math. Some people maybe have some apprehensions about, I don't know why you would, but right, so then we have math. Right? Math is like, maybe it's dying because you just have your computers do your math for you now and just have the computer tell you the pressures, et cetera. But right, we still learn some of the math concepts in this course. Okay? Now, I just have a grab bag or your toolkit that I think of that you should have in this class. And really, it's true for almost all engineering fluids classes you'd have, right? So here's my list of toolkits, I think, of things that you definitely need. So from we have it. What do you need from algebra? Concept of solving n equations for n unknowns. Right? That concept, remember a lot. Where you have n equations, you have n unknowns. So if you have n unknowns, you have to write n equations. That trips up so many people in some exams I've given, where you can make an undergrad spin their gears over and over again because the solution is just that they had to write down 2 equations, and they're just trying to solve for 2 things with 1 equation. So having that concept firmly in your head, I think you definitely should remember for algebra, right? One I say is writing one in a clever way. That's kind of just something, right? I mean, I don't even go over that. You'll see it, though, and I'll point it out later in the class. Pretty math, which really is factoring, right? How to factor polynomials is super important. Or just even simpler things, like even just something like if you have a plus b, just going in your head, I could also write this as a times 1 plus b over a. It doesn't seem like a big step, but that's just a tool you have from algebra going, I can pull the a out or factor an a out, and now I get this term. Why would you want to do that? Well, you'd want to do that because sometimes you would know from the physics that this is a small number. So it could be like neglected, essentially. But you'll see more of that later. Okay, anything else you need from there? Oh, yes, and then I have no zero below, right? Just can't have 0 in the bottom of a fraction. Just remember that. If there's a polynomial in the bottom of a fraction, you would know solve it for 0, and you get critical points, or something crazy happens there. And what else we have no, right? And no negatives under a square root. Remember that. Again, these things just hold in your head because if you do come up with an expression that has something like that going on, you go like, well, can't really do anything else, but I can say something crazy goes on when there's 0 on the bottom, and you can't say, well, I don't want complex solutions, so then you solve this sub-problem. So that's what I think algebra-wise, the things that you should really learn. Now calculus, what should we learn from calculus? Or carry over from calculus? I just have product rule, chain rule, power law, integration by parts, and then U substitution. Those are sort of the 5 major techniques and tricks you learn in calculus of how to solve, product rule, chain rule, power rule, just super helps to remember those exactly, right? Which one's the most important one? I can't really pick. Integration by parts is always like forgotten and hated, it seems like, in calculus, and not used that much. Ends up being a nice little trick also to have. If you have an integral, you can swap a derivative over sometimes and use it that way. And then u subs is just like, and then remembering u sub, this is the hardest one because there's no like algorithm for it. Just the goal always with u sub is you're trying to make your integral look like an integral in a mathematical table, right? If you can substitute functions, et cetera, to make the integrand look like something that you can look up at a table, then you can solve your integral. So that one's hard, but you just keep doing it to just kind of see what works and what doesn't work. But certainly, that's a big one. Product rule is one of the super most important ones as well, remembering it. And these actually, you can get integration by parts from the product rule, right? Because right, that's the product rule. And then, right, if you don't remember what integration by parts is, and sometimes I always immediately forget what it is too, I always remember product rules, so I'll get this by just integrating this. So if I integrate this whole thing, right, this integral takes away that derivative, so now you get fg on the boundary, let's say. I don't know, whatever you want to label this. Sometimes I go like boundary. And then, right, now you just have this relationship of a negative, right? I just moved one integral to the other side. But again, if you can't remember what integration by parts is, just remember the product rule and integrate the product rule, you get it. But also, I also remember it a lot because what integration by parts is doing for you is you're moving an integral, you're moving a derivative over in a product of your integrand, right? So see how I have fg prime, and then what integration by parts does is you tell yourself, I want to move that, like I don't like this g prime, I'd rather move it over. So integration by parts does that for you because you move the prime over to this f, and then you have this boundary term. And a lot of times you do it because, well, you say your function, one of the functions is 0 on the boundary. So you can get rid of that term and then just have this negative relationship. All just little tricks, right? Just little tricks you should remember along the way. OK, and then what I want you to remember from differential equations, which is also pretty sure it's a prerequisite. What do we have for differential equations? Well, the biggest thing all engineering does is separate and integrate. So all these terms, I'm not writing them down because I don't just look them up, refresh your memory. You do that process. Okay, and then you have integrating factor. Right, or first the first order ODE solution. You get it through an integrating factor, but the idea being that there is basically like a quadratic formula for first order ODEs. You can just write out the solution if it looks like something. You don't have the luxury for a second order. And that's the other thing you should remember this is that second order ODE with constant coefficients. Right? This is just the damped, right? The mass damper system, right? But remembering that solution, right? So this is A, right? Or even F in there. So this can even be solved if you have actually like an f of x here, and that's where you do this, the transforms. But just these being constant coefficients. Remember, right? Remembering what that solution looks like is important. Notice that you don't get it if it's constant functions. Educated guess. Right? The educated guess being you have a differential equation and you say, I'm going to say, right, this looks like, something like this. Remember you did this where it's like then a bx, and you plug this function form into your differential equation and try to solve for things that way. You don't do it enough in the class, but I think it's important because most differential equations end up getting solved that way, where you just go like, what if it looks like this, and then start solving it. So that's super important. And also another one that is not is classifying the differential equations, right? Just the nomenclatures of naming them is important, because if you get to your governing equation, it's a differential equation, then first step is you should label it and classify it, because that gives you a better way to look up how to solve the beast if you can just classify it. So knowing the nomenclature of how you classify differential equations, is it second order? Is it nonlinear? What's the highest order derivative in there, et cetera? Is it non-autonomous or autonomous? Like key terms like that, just knowing that language, I think helps a lot. Okay, so that's my toolkit I think that you should have for this class. Okay. Certainly, if you think I'm missing one, let me know. I also think that beyond math, you should know how to code. Python. Right? Knowing how to code is critical for any self-sufficient scientist these days. I think it's ridiculous if you just say, I don't like coding, I can't do it. You'd be falling behind, right? Knowing how to write a program is very critical for any sort of quantitative science these days. You're just falling behind if you just don't want to code, I think, in this advanced field. So I would say use this class to learn how to code MATLAB or something like that. Even if your plots aren't the best, I'd rather you go through the struggle of learning how to do these languages, right? And then I can just say, the plot looks bad. But if you went through the process of like typing it out, that's super critical. Okay. That's what I have. Perfect. I'm on track. So next is my little soapbox of why we're doing why math, why analysis. At this point, computers are so awesome these days that we could just have any fluid problem. Remember that step where I was talking about any fluid problem. You could just have it where you draw your picture, right? You set up some STL file, and you have some computer just solve the total nonlinear Navier-Stokes equations and then calculate what you're looking for. You could do that almost with a lot of systems these days. And there are a lot of programs that do that for you. But should we just give up on the math? Should we just sort of go like, well, integral analysis or differential equation analysis or writing out the Navier-Stokes? It's just too hard. There's just no point anymore, right? JARIS, star CCM, right? ANSYS, they do great for me. So I just have a grab bag of like things that I think answer that, and they're really sort of a compiled list from my advisor and myself. But right, so let's maybe some reasons is that as force so if you're going to do the analysis, right, a force balance. Right, force balances are intuitive, right? And what that means is if you just do the analysis and you do some sort of force balance, before even solving things, just thinking about what forces are happening, right? You're almost your own CFD solver, right? You almost just know like what the direction of the flow is going to be. Like all these things just come about from just drawing the force arrows and balancing them that way. One other thing is math. Right? Math is cheap, right? It's essentially free. Right? And CFD is cheaper. It's getting cheaper all the time. There are a lot of good open source softwares. But even if a CFD program is free, right? Excuse me. CFD equals a lot of your time. You will have to spend a lot of time learning how to use that programming language to maybe just solve one problem. Right? And then what else? We also have that it guides experimentation. Right? If you do the fluid analysis and you do this force balance concept and you do this Navier-Stokes killing off terms, etc., you can make a prediction that the flow is governed by these things just from that analysis, and you could stop there. You then, from your math, could go like, it's probably going to look like this, and then move on to the numerical analysis, or then move on to actually running some type of experiment. Because there are even lots of things where CFD is just not, it'll take far too long for it to calculate that. You just have to spend the money to do the experiment. That being said, experiments are the most expensive. Right? The experiments cost a lot of money, right? So if you're going to run an experiment, I would say make sure that you almost know the result before the result happens. If you don't know, if you're surprised by the result, that's awesome. You're clearly going to get published if that's the case, right? But usually I think the case should be you make hypotheses based on the math, you then maybe tweak around numerical stuff, you then do an experiment, and it just confirms what you already knew was going to happen, right? But it's a confirmation, publish that. If you're surprised, even cooler. That's like a Nature article right there, I think, right? If it's just a totally non-intuitive thing where it's not happening how you think it's going to do. Those are always awesome papers that are always totally appreciated. What else? I have fundamentals don't change, right? The fundamentals. Right? The fundamentals of these equations have never changed and never will. How they're implemented will change. So if you understand the language of like how the fundamentals are implemented, how they're derived, then you will understand how something has to solve it and how something has to verify it, right? It also just, right, and my advisor says it's right, major errors right, major errors that occur all the time, they end up always being some fundamental mistake that went wrong. So, so if knowing the fundamentals, knowing the math is really important for that reason, that you'll make less errors because it's not usually a minor thing that someone messes up on. It's usually a really big thing they messed up on, right, or a fundamental reason. And also, I think my sort of take on this is really, I think, right, science. Your goal always is your goal as an engineer, right? You're really producing plots. You're producing some figures that help someone make a decision, right, for their company or in the academia. You're trying to populate some plot, right? Excuse me again. Okay, so I think this plot should always be three things, though, right? You should have your theory. So this is your math. Some type of theory. I don't care how you get something like this. And then you should have, right, I want data around there, right? And these plots are very expensive, right? I want that around there. And then I also still think that we should have, maybe it deviates off a little bit, numerical, right? You really should have all three. I think not even having a little bit of theory sometimes is just like, it's not enough. I mean, science is accepted on the basis that so many things agree this has to be right. So missing out on that theory bit is I think, a disservice. And then I have more in the notes of, I have more in the notes of reasons, but I kind of want to get to this toy example that we're going to do. But a bigger, right, beyond that there should be all three things. I also think that, right, some math solution solves an infinite number of problems, right, based on parameters, really, right? So if you solve the fluid problem and you have some expression, you actually solve an infinite number of problems. And more specifically, it actually tells you the effects of initial conditions and boundary conditions on the solution. It's just something that you may have noticed if you run numerical simulations ever in your life or have done your CFD, is sometimes you'll spend a lot of time setting up the solver and then run the solver. Now run it again, now run it again, now run it again. So you have to run every time. So a numerical solution, right? It's one problem you're solving. One initial condition, one boundary condition. So a numerical solution, you solve one specific problem with one initial condition and one boundary condition, and then you integrate forward. Right? You integrate forward in time, and then you see what happens. Right? So while numerical solutions are very awesome, and I think they're really hard, and I think they're really awesome, but I think the only thing left, the only defense that you maybe have left for math analysis or math solutions is that concept right there. Because I certainly do, when I do programming or CFD, I get kind of annoyed of having to do this like, set up the BT, run, set up the initial condition, run. Or like now you have to, or you can sometimes write like a JavaScript program that like sets up a batch of initial conditions and boundary conditions and runs them every time. But then that takes forever too sometimes. So this concept of if you can kind of approximately solve just any statement of math, it will give you an infinite number of solutions. And that way you can solve like just a whole class of solutions will be solved. So there's certainly something worth doing it for. Okay? And it is an old technique. I mean, this stuff has been going on since the Greeks, people have been solving fluid problems, right? So it is really old, and computers are the newest thing. Computers will probably replace all this math stuff in the coming years because they just keep advancing. So, maybe there's a world where no one even does math by hand anymore. And it's almost looking like that way. I mean, I use Mathematica all the time. I don't calculate integrals or anything by hand anymore because there's just too many mistakes. But, right, symbolic computations, right, symbolic manipulating software is still an aid to getting like your math solutions. But I mean, everything goes away at computers. But more so, I think it's just this idea of the fundamentals of these solutions are really what guide design and analysis, right? And if you know the fundamentals and you know the techniques involved, you can catch errors, and it's also cheap, right? This is also, you can't forget about this. This is cheap. If you're at a company and you get hired, you can sometimes solve incredibly difficult problems with just a little bit of math. And then you'll be considered like this, oh my God, how did you do that? That's amazing. But it's just like you just knew some little math tricks to just really say this is better than that, right? So there are more reasons in the note which maybe, certainly go over them. It's just a soapbox of, I think, why you should be excited for this class, why you should want to do the struggles of all these hard things. You'll just have a better understanding of fluid flow if you go through these things. You can sometimes have a good sense of fluid flow if you just run a bunch of CFD experiments, but I don't think it's as good as if you looking at the solutions and deriving them. So that being said, let's do a little toy example problem. What's my time? Okay. Let's do a little toy example problem then to sort of introduce you to what it will kind of look like in this class. What do I mean when I say let's solve some fluid problem? Okay, so this is a good one. Let's consider a liquid slug in a U-tube. Okay, I will just hold my notes this whole time because I want to get this good for you. So, liquid slug in a U-tube. I'm imagining that everyone knows this nomenclature, that P is for pressure, etc. I'm going to measure coordinates from here. Right. So again, I'm already giving you this well-posed problem and So kind of think about those steps and how I've already started past a really hard part of analysis, and that is, let's say you looked at this and then said, how can I make that a well-posed problem, right? So here's my x coordinate. I'll measure from here. Here is the liquid. Right? I want to look for this height as a function of time, right? Because I see it oscillating where it's like left, and I just go whoop, 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 whoop. So you go, what is this? How can I characterize this oscillation of the fluid right here? Let's say this is so the pipe itself has a radius. maybe it's, let's say somehow it starts off like this, so then you let it go and you see what happens from there. So this means something too. So I want to see h of t, and then right from here we're going to say as well, one thing I know is that h of 0 at time equal to 0, I will say this is equal to negative h, because I'm going to say this is measured down. So that's a problem setup, right? It's already skipped the steps where I've had some oscillating things. I've asked myself, how could I characterize that or model that? So I've had to draw this picture. And then after this picture, I then had to say, what am I looking for? Well, I'm looking for the height as a function of time, because I want to see, how fast is it oscillating, et cetera. Then I had to draw this picture where I gave dimensions. I know this is twice the radius. I know I have atmospheric pressure out here. I've defined the function that down is going to be positive because it's just going to work out better. And then you even have to go the step of going like, well, initially it starts at some height h. So that means in this function, I know h of 0 is negative h, some height value. Okay? So how do you get motion from fluids, right? So right now, we won't have Navier-Stokes equations. Right now, I'm going to say, what if you just know right? Let's just say you only know, right, Newton's second law, right? The glorious, wonderful thing that you learn in physics too. Don't have Navier-Stokes. We'll have a more specific way of doing these things, but for right now, you just have this. Now, what is A? A is the acceleration of the particle or the thing I'm looking for. And A for me is actually this height. So one rewriting of this will have some mass. So H double dot is going to be the sum of my forces. So made a little bit of progress right now, okay? We've gone from at least I know the A in F equals ma is going to be this height function I'm looking for. It's a function of time. There'll be some acceleration having into it. That's what the double dot's for. So now you get to this part, and this is sort of the brainstorm part. This is a very simple example, but I think it illustrates so much of what we kind of do when we look about fluids and think of the forces happening. So brainstorm now what you think the forces are going on right here. Okay, so in the class, usually I stop and ask people, what do you think force is happening? How about you? What's that force? How about that force? Give me another force, another force. And we would come up with a bunch of forces. Right, but for now, I'll just cut to the chase. So let's say someone could say, well, there's the force of gravity. There is a viscous force. I'm assuming that you've heard of viscosity. No, there's some force involved with it, so there's some force due to viscosity. Well, and then let's say someone goes to the force due to surface tension. Let's say there's the force of the gas, right? There's the pressure force from the atmosphere pushing down on there. Let's say, I think someone even said this one. There's the magnetic field of the Earth, right? Let's say there's a Coriolis force, because even in this U-tube, it's on the Earth and it's rotating, so there's some minor Coriolis force happening because of the rotating frame. So how about there's that? Let's say there's a force of, so magnet force. So you would just keep listing these things out and out and out because you're just brainstorming to go well, what's going on with this thing right here? Okay. And then there's this process of you go, well, this one doesn't matter. Clearly, the force of the gas doesn't matter as well. The magnetism field of the Earth doesn't matter. This experimental step isn't big enough to even observe the Coriolis force, so it won't matter as well. It's very simple, but the process of this idea of listing out all of your forces and going no, no, yes, yes, yes. Okay. Now, before we move on, I should mention that pay attention because scaling does this. Right? That step of crossing out actually is something that scaling or even non-dimensionalization does for you. Right? So let me say that too. So that's why you should learn it and be good at it, because it lets you generate a bunch of cases and a bunch of forces and then go sort of quantifiably, those don't matter. What matters is probably just the gravity force acting down on the floor. And what probably matters as well is the viscous force, because it's a very viscous fluid. I mean, let's say it's almost honey or something, right? Or glycerin, right? Let's say it's not like a I don't know. I mean, they all have viscosities, but it's just, there's just, you know, you could make some statement about like, well, there's just some viscosity happening in there. So clearly it's this viscous force occurring because the wall, no slip, blah, 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 would have to matter. Okay, so you've done that now. Okay, let's subdivide again now. So I have two forces I have to now prescribe, because what does Newton's second law says? Newton's second law is really a statement that forces prescribe motion, right? But it's loaded almost sometimes, because then you have to think about like, well, how do I model the forces? So then you have to go about and then separately ask, how do I get that gravity force? Okay, so so gravity force, right? Mass times gravity. This is really a vector, right? But let's just say clearly it's in, right? It's only in the direction occurring right here. So here's the gravity vector, acceleration vector. Okay. So then, right, you have mass. Well, what's the mass? Well, I have a mass of a fluid. You just, go, well, it's rho volume g, right? Okay. And then you go, how do I rewrite volume? Well, I know it's an area times some linear dimension length, g. So what's L, right? You go, well, the volume I could get, this is L. So if I have the cross-sectional area, I know it's constant. Over here, it's 2r. Let's say it's approximately constant throughout the whole thing. That would be your linear dimension. So then you rewrite volume just in terms of other dimensions, a and then times an L. Okay. So then with that L, right? Well, then what's L? Right? So it's really right, knowing this length, because it starts off here, it'd be even, right? Really, it's a conservation of math concept, but really, I would actually know this length from this function, because all I really need to do, right, is just take away, right, it's going to be negative and that's because of the symmetry. That's because of a symmetry argument on there as well. Right? So that's great, right? That is one of my forces. I'll leave it up there. Got one. Now, you have another one to deal with. I need the viscous force. So the viscous force is a little more, right, it's a little different. You'd have to then make more assumptions to figure out what that viscous force is. So one of them is you could say, well, what if it's laminar? Right, you're going to say you could say it's laminar flow, you could say it's turbulent, but you'd have to make some statement about it. And then you'd also have to even say, right, I'll also say it's fully developed. Right? And you're saying these things because you have enough experience of what all these terms mean, and you have some intuition of how this thing was moving as you observed it. You're then going to make these statements. So then when you have those statements, you then can go to like an argument of what you can say, what you can't say. Well, if I have these conditions in some cross-sectional area, you would know that I know the change in pressure looks like this. And that'd be the change in pressure right across the tube, right? Okay, right? So this is something you know, and this thing is Poisson's law that you get from some Navier-Stokes analysis that you're going to do. But you could start from there. Maybe you remember this. You Google, right? You can Google something. You can look up viscous forces. You could look up fully developed laminar flow in a pipe to help you get maybe this expression, okay? And this would be the change in a force over area, right? Which is really a change in force pi r squared. So that would be So this side, I'm trying to rewrite this side. And then what about flow rate? Well, flow rate, or volumetric flow rate, is what Q is, m dot's mass flow rate. But in incompressible terms, we always use a Q, right? So you'd have a change in volume over time is really volumetric flow rate. So let's rewrite that again. That's a rho A H. That's what volume is, dt, okay? Okay, all of these things together then let you say that this where's the dH dt come from? Pretty clearly it comes from here because let's say the rho is constant and the area is constant. So then those come out of the derivative and you're left with a dH dt. Okay, it's clearly at some velocity that occurs. And then the other substitutions let you get here. So that'd be for laminar, right? Now, another one you can actually do is you could also look up like, semi-turbulent, right? So if you had a Reynolds number, which I imagine you know how to calculate, right? Let's say it's greater than this. You can just look up some proportionality thing. Where it's a velocity, right? But again, you would, right, if you had some more rationale of what's happening in the flow or the speeds happening, you calculate a Reynolds number. That helps you talk about laminar. Fully developed is a different story, but we can learn more about that later. But if it was bigger than that, you could also make a different substitution for the viscous force just by saying it looks like this. And again, this comes from Googling. This comes from saying, what's my viscous force look like? What do I have to put in this expression? This one's the simplest one because it's laminar fully developed. You can even do some derivation stuff to like get what the dH dt is. But of course, you can also just look at what other people have done experiment-wise to categorize or to prescribe forces based on other dimensions. So another option for this same problem is to say this, that it's pretty fast, right? It looks like it's oscillating pretty quickly, so it's going to look like this. Okay. So that's sort of like that's a big step that we've made, right? You drew your picture, you drew the forces out, you neglected forces because of, right, let's say your awesome intuition you have of how fluids work, and then you even categorized all your forces in terms of this function you're trying to look for, which is the h of t. How much is this oscillating by? Okay, so then let's put it all together. You had the NA, everything, you had those minus signs, so everything together will be this. Okay, that's your ODE, governing equation. That's the governing equation. And you got to it from a force balance. Navier-Stokes is just a much more specific way to get at these governing equations without having to think about the forces. But certainly starting from forces helps. And then here's the differential term right here. Right? Maybe you recognize that ODE, right? Certainly, I hope you would recognize it, right? But you can classify this thing as well. So let's go through that process. Let's classify it, right? So this is constant. Remember, the L is set for whatever it was initially. So that is a constant. The little trick of making it 2 minus h is just a way to make it look like h. So constant. What's the highest order of the derivative in this function? Well, I know there's two derivatives in time for the h variable, so it's second order. Homogeneous. Okay, because it's equals to 0, so we say that's homogeneous if that's the case. Constant coefficients, also important because it makes solutions a lot easier. So you say it's a constant coefficient, you learn how to do something like that. There are other things as well. The biggest one is that it's linear, right? Noticing when a governing equation is linear or nonlinear is a big skill that you should learn. And some people have a hard time doing it because they mistake powers in the derivatives for powers on the function, right? Nonlinear terms are things that look like this, right? This is nonlinear. This is nonlinear. This is nonlinear. But this isn't nonlinear because the squares are just on the operators. So for this function, we actually have a linear, second-order, homogeneous, constant coefficient governing equation. So that's great. That's totally solved. You can look up the solution if you want and then write it down. But hold your horses because they still have all these pesky dimensions, right? And then the other thing we haven't really done is also any ODE, right, has to come with a set of initial conditions, right? So we know one of them because we already said it, right? That is, it starts off at a height. So that is an initial condition for this. Since it's second order, I also have to prescribe, right? That's another reason you should classify, because it lets you know what are my initial conditions or how many should I prescribe. Do I have a boundary value problem? Is it an initial condition? Those are different things, actually. So for now, this one, we're going to say it starts off at 0. You were just going to say that. How could you? I mean, it's kind of strange, right? How would you lift this fluid up to a certain height and just drop it? I don't know, but let's say you could. But not terrible. You could actually put a velocity in there, but it makes it different. But this is really saying how fast am I initially going? For this problem, let's say it starts off at 0. So this is now a totally well-posed problem. Totally solvable. Totally integratable, and everything great about it is great. But we're missing one other thing, and that is this, right, the dimension things, which we should get to. Should I leave this up here? I'll just do this one. Because this, we changed f equals ma into that, by the way. Really, that's all we did. Remember, put that in your head, that really what we did is we turned f equals ma into a differential equation. So non-dimensionalization is something that we can just do through scales that we can call them, right? So the idea being, what value do we suspect h to be around, right? And that's, you have this notation of, I'm going to say that h scales like this height right here. Did you have any other options? I mean, you could have said that the height's going to scale like the radius of the tube, right? But I mean, that would be like if h and r are the same. Usually this occurs for really kind of thin tubes. So, right, if this is really thin, you certainly at least could view or see that the height isn't oscillating like just a little tiny bit. You could maybe see that it's like, kind of going around right, this h value or initial condition height that I gave it. So that's going to be a scale that we use. Also, what you can do is you can also just say, right, it's kind of the only option you had because of your initial condition that you gave. If you're going to say that h is around some value, the only value you actually know of what h is your initial condition. So that's a darn good choice, I would say. So that's a good place to start. So we have that one. But then there's other thing is like, well, what values of time do I usually see? Right? Sort of think of this as the frequency of the oscillation, maybe. I mean, you can think of it that way, too. Like 1 over time looks like what? And that would be a frequency term. But you could also use time. OK. Now, we don't have that time is the problem. That's this idea of using the differential equation to solve for it, right? We could assign this value. We could assign the height value here because we just know, well, I'm going to say this h function just kind of varies around that capital H. Clearly, I see it, and it looks like it's around there. So that's going to be a scale of non-dimensionalization I'm going to do. Now, what non-dimensional means is you're saying that I'm going to say h star, which is non-dimensional, is just defined by this. So I'm normalizing all of my dimensional values of h by my h, right? And this could be, right, I mean, what you're really saying is that this number is close to 1 is what you really want, right? Because, for instance, I could have said I could have said that I'm going to say h scales like the radius. Let's say it's really, really thin. Well, that would mean now a non-dimensional star, like this could be like 10 or something, right? It could be a bad scaling, or right, this could end up looking like 0.001, which you say is bad, right? Because whenever you do this process of non-dimensionalization, what you want to end up happening is this number's like 1. And like 1 is sort of like, well, like 1, 2, 3, 4, 5, maybe up to 9. That's like an order 1 number. But you certainly don't want it like 10 or 100 or 0.0001. So that's your estimate on h. But the time. So the time we don't know, but you can solve for the time scale, right? So solving for the time scale comes from this equation itself, okay? And this, maybe you've seen this before, maybe you haven't seen this before, but what you're going to do is you're going to insert then the scales into this differential operator and see what happens, right? So you're going to say that t scales like a capital T, let's say. You don't know what it is, but we can solve for it. Okay, so rho a L, here's a d squared. Here, right, recall that this means that h star, that h star's non-dimensional height is actually equal to dimensional height over this. So one way of thinking about this is actually that, right, you just move the h over here, and this helps. Because now what you do is you're turning this differential equation into a non-dimensional one by just straight substitution, right? So here's the h. Same thing goes for here. Okay. So from there, you just kind of move, right? You then move the things around, and then you get, right, now you get a non-dimensional Sorry for the dead silence. Okay. I'm going to put these like this. Okay, what you've done now is you don't know what the time is, but you've inserted this, so you know that these terms, these terms are non-dimensional because of the star notation, right? Now, again, what did I say about, right? What the idea about this scale being it looks like 1 is important for maybe this argument happening right here where you say, this looks like 1 now, this term looks like 1, this term is approximately 1, and now you're saying this differential term is approximately 1 as well. So now saying that, you can now focus now on these parameters and coefficients and make statements about, is that big or is that small? Okay? So what you do for that is you then just kind of drop you drop all the differential terms now, because you're now just talking about the relative size of these parameters, these coefficients. So what you do there is then you make this sort of A, L, H. I do a comma, some people. Technically, I'm not allowed to do that in this world of scaling, but I just always kind of remember it like that. So now I just have these coefficient terms to look at and analyze. The coefficient terms being what is the size of that number? Okay? Now notice, though, that these are also things that you can measure, right? So I know what G is. I would know the density of my fluid. I certainly know what A is. I definitely know what H is. Same with this. This is, right, you can measure that, L. So you can even like plug numbers into these quantities. You didn't know anything really about the dH/dt thing, but you certainly know what these coefficients look like. The one you don't know, though, is this time. So that's this idea of solving for it. Now, how do you solve for it? Well, the other thing is what you have to do is you have to say, well, two of these things balance. Pick two and then solve for one. Okay? So recall as well what each of these terms meant, right? Each term it came from somewhere. And where did it come from, right? This was the inertial term, right? This term came from, right, F equals, this is the MA part, inertial. This was my viscous term. And this was my gravity, right? Each of these coefficients came with an associated term of a force. So remember that when you do maybe these scalings, right? How many comparisons can I make of these numbers? Well, there's 3. Choose 2. That makes 4. Or 3 if you do all matters, right? So I can do... I can look at what is the case when the force of gravity balances the force of inertia? What does it look like if it is just F equals ma? Or that these numbers are around the same, these numbers are about the same size, while this one I know to be much, much smaller. Okay, you could also do inertia could balance the viscous force. What if ma really was just dominated by this viscous force? What would that mean? Well, if you're a fluids person, you would say that'd be really impressive because that would mean that the viscous force is governing, right, the inertia. So that means like it has to be super, super viscous, right? That'd be absurd. You could also have, right, you could do, what if there's no inertia happening? That would be viscous, right? It'd be viscous balancing gravity. Okay? So all of these terms come up with something, right? And each one of them actually comes up with a time scale we can solve for. Okay? So let's solve for these time scales. That's what, right? The idea of this meaning, you say that this term balances this term. Okay, so that would mean keep the squiggly balance line. Okay? And now we can actually calculate, right, in terms of this squiggly, right, similar line, we can calculate what the time would be. So I cross out the H's, A is gone, even this one's gone. Okay. Perfect. So then this would mean that my time scales as Sorry. Okay, see how we calculated now a value of time, right? It's time scaling as L over 2G. Now that number you can plug into a calculator, right? You can plug this number into a calculator, right? And you, again, can check that's what you want to really be happening when you're doing this. Because you need all the non-dimensional time and the dependent variable to really be scaling by 1. So you could check that one too. How about this one? Well, inertia balancing viscous forces. So that means that the inertial term is really balanced by this. Pi L T. Leave a T. H gone. L gone. Pi sticks around. Okay, so that would mean that the time scales as what? I just want to make sure I have these right. Everything's in the notes as well. Again, you could check this, right? And maybe you can get a better sense of how this, of what you'd be doing, right? Because even just looking at this, let's look at this one, right? Square root of L over G. G is about 10. L, you can even estimate that way based in like meters. and then it's a square root. So this could be a small number, but square rooting small numbers makes them bigger, etc. Give an estimate, or just plug it in the calculator and do it that way. But for this one, again, like this is usually 1,000. This is a small number, but then I divide by the viscosity, and these numbers usually end up being pretty small. So that's going to be a pretty big number. But again, you can also just calculate it. How about viscous gravity? Well, I'll just cut to the chase. Right? And really those arguments before even cutting, you would have this is, right? See how this is now small, right? This is, right, super small number, L, now dividing by 1,000 times 10. So this is, right, this is going to be super small. Long time. So even just those scales of balancing those forces, you get a sense that, well, I have like order 1 time or seconds. I have like, I'm looking at seconds in like, what does the system look like if my clock ticks in seconds? What does my system look like if my clock ticks in years or minutes or hours? What does my system look like if my clock ticks around at milliseconds or nanoseconds? That's what these are telling you. So again, it's pretty cool. This is a very simple example of just a second order ODE. But just, I think, conclusions based on that. These are physical things. I can measure them. I went from my ODE. I non-dimensionalized it. I'm now just looking at the coefficients. And then I make comparisons of those coefficients to calculate my time scale. And then when I calculated the time scale, I could see this one's around seconds, this one's around hours, this one's around nanoseconds. So I don't care about the hours time scale. When I look at this, I go 1, 2, 3, 4, 5. I care about that time scale, so that's the good one to look at. But certainly if I do care about really short times, I would know that this is the system I want to model it as. Okay? So that is sort of that is something that you maybe can see right now, what we're doing, is that you're trying to get that idea, that concept in your head is you could have very complicated differential equations, but if you can make some physical arguments about how they run, right, then you can move along with it, right? So essentially, after you do this process and you find the time scale you care about, you then would substitute that value, right? Again, we claim this, and now I'm looking for what this is. So let's pick one of them and then, put it all back in. So which one are we going to do? In the notes I have, which one did I pick? So let's do this one, because I already said I cared about the seconds. You could do the other ones if you want, and maybe you should do it as an exercise, but I'm going to say, okay, because I solved for it. So let's go back to the gravity equation and plug that time scale in. And then when you do that, you're going to end up with this. Okay? So I would say you go ahead and do that substitution. It's in the notes, you could copy it as well. But I would say maybe pick a different time scale and do that algebraic process of subbing this time into there, right? And then do that substitution where I know that time is equal to my capital T times this. So in this case, right, everywhere I saw that, I substituted this in. And I got expressions. And this ends up being what you get, some term. Now, the check that you should always do if you do this step of re-putting in your time scale is this. I said, right, the time scale I picked was what? It was these two terms. It was my inertia balancing gravity. So after you do your substitution, it should always be the case that that there's just ones in front of here. Because you said those things balance. Those things are like order 1. This is where you should have the parameter, right? If I did that substitution and I saw a term here and I saw a term here, I would know I did something wrong, because the whole thing began with me saying that these two terms are basically the same. They basically just have a 1 in front of them, but this one is the variable 1. This has the slight effect of viscosity in this system that's coming from this oscillation. So check yourself when you re-put in your scales, right? Because if you're claiming that these two things balance, after you do it in the substitution with your non-dimensional equation, well, then these two terms should balance. They should look like 1. Okay. But this is great, though, because now, right, this is just some, expression. I don't even care about anymore. What I care about is that it's just a number. Call it b, right? It's just a number. We're just going to call it b. It's an integer value. There's no dimensions associated to it. No dimension, no dimension, no dimension, and 1. And then also look at the boundary conditions, or the initial conditions, I'm sorry, right? Here, 1. Well, 0 divided by anyone is still going to be 0, right? So then even look at that system. This is awesome because this is like things you solve in your calculus course, right? That's stuff that you solve in your math classes. Just weird, meaningless types of equations with like maybe this one parameter in there. But now you got there. You got there from talking about physical scale, saying it looks like h, right? I know that h of t is going to vary around this value because, better you're just seeing it and looking at it. That's the phenomenon you're looking at. You went further and said, my clock is ticking at t, so I know I know it should look like this. Then you arrived here, and now you just have this parameter b and then h. Now, I want to go into another thing about like pretty math, or noticing things from an expression. Okay, so this is what my b value is. But in terms of fluids, a lot of times you want to get expressions into like known non-dimensional variables, right? Or see if your non-dimensional term is related to like really classic ones, i.e. you're looking for, is there a Reynolds number in there? Is there you're looking for like, can I express this in terms of a Reynolds? Is there a Weber number, a capillary number? Doesn't matter. You'd want to have it look like that. And this is fine and dandy, but like it's better if you can get it in terms of like a known non-dimensional number based in the class theory, right? So that's just this trick. So I knew that b is this. Okay. Okay. A gets rid of the pi. I just rewrote what A was. What else can I do? Then there's this trick. Okay, this is right. So I have an R right there. I pulled it over here to have this L, right? And then I pulled that one R into 2 square roots because this is an aspect ratio, right? Sometimes we call this aspect ratio. This is interesting. But then this is actually, it turns out to be 1 over a Reynolds number. Okay, because the G, right? Because there's a G in there somewhere. Okay? So this process turns out where this, I'm going to say, is my aspect ratio. Commonly, you call that an epsilon. Remember, in the picture we had, the L certainly looked a lot bigger, right? The L certainly looked a lot larger than the radius, right? So this is actually 1 over an epsilon. So it's actually a pretty big number. But it's square root, so it's kind of harnessed by that. Okay, and then this comes around, you have to like kind of look at this G in gravity. So you have to express that in terms of a Reynolds number. So how did I do that here, right? I mean, a velocity can be looked at like that, right? or r is a dimension, not Reynolds, right? So this velocity, if you're looking at in there, there's a u. It's a value of velocity. So it could be a Reynolds number, actually. So this is sort of just another way to rewrite this coefficient b. You now can make an analysis based on the laminar turbulent thing. But then watch out also, because what's tricky about this stuff is you already made the assumption that the Reynolds number was pretty low, because you said laminar to get that force value. So really, this is only true if it's really small. So you can vary this r within the laminar assumption. But at least it is, right? At least you can have that relationship in there. Then the other big one you have is this epsilon, right? So this governs a lot of things happening too. Okay. Square root's important because even if that value was 100, right? Square root of that's going to be 10. So these square roots, think of them as dropping large numbers, right? That's what our point of them is. So it's just a good expression, right? And that's this idea of just taking your non-dimensional coefficient term and just working it more, getting a little more terms out of there, getting a little more expression out of there. So that's just that example. And that's that idea of this algebra pretty math stuff you do. You can look over the notes and go, how on earth would he get that expression to look like that? That's crazy. Well, you get it from just like this desire to make it look like a Reynolds or make it look like some sort of known parameter. Why would I expect there to be a Reynolds number involved in here, right? Well, I would hope that some of you would just go, and it's probably going to end up in there somewhere. So let's say this is really, sorry. You know what? So I noticed in my notes I had this, but this is wrong. Like, sorry about this. So on epsilon, right? Usually an epsilon should be the r over L, because you usually say epsilon's a small number. So this actually looks like this. Okay. It's actually and then a 4. Sorry. Okay. Look over that. I need to correct that in the notes, but I hope if you watch this, you would see. It doesn't really matter. The whole point, I mean, what matters is really this with this r. I mean, this b, right? So really, b kind of scales like 1 over a Reynolds number. But why should a Reynolds number come up, right? You should know that, right? A Reynolds number is a ratio of inertial to viscous forces, right? That's exactly what this is, right? When you did that balance, right? You had this balance now where this is a viscous force, and you have an inertial force, right? So 1 over the radius makes sense because 1 over the Reynolds number makes sense because that's exactly what this ratio is going to be. This is the viscous force, and I divide it by the gravity force. So 1 over Reynolds number. You should expect that. That's what I'm just saying. If you have the intuition of what these non-dimensional numbers like Reynolds or what they mean force-wise, you can then be on a better path to make your term expressed in terms of like that, right? No one cares if you published a paper and it looked like this if it just was B. Now, you put your parameter in terms of Reynolds number, or capillary number, or a Weber number, or a Strual number, whatever like that. Now the fluids people know what you're talking about and go like, wow, I didn't know that parameter popped up in there. So it's a very key step, I think, for communicating to other people that do fluids to make sure that your weird math expression has those non-dimensional numbers in there. And the only way you can do it is just fancy math and fancy trickery. So that's great. Maybe I hope we've learned something about how you can go from forces to get to this, right? This idea of analyzing your differential equations. I mean, this is right? This is B, right? Call it like that. Let's say it's like this. Because you already made the statement that the Reynolds number, right? You already made the statement that the Reynolds number was laminar. So let's say it's less than 100, right? Well, if that's true, right? So if I just see characteristic velocities and Reynolds numbers less than 100, this governs my oscillating fluid flow, my oscillating tube problem, right? And I can vary this too, right? So, right, I can make this super, super dominant, right? If this is going lower and lower and lower, this number is growing and growing and growing and growing, right? But then it's a battle too, because now I have this epsilon, right? This 1 over epsilon. Remember that epsilon we're going to say is r over L. And we just said that, right, this is definitely, right? we're saying this is definitely less than 1, let's say. I certainly don't have a radius, right, a radius of a tube the same length. Like that doesn't, so, right, my tube is definitely going to obey this. So see, there's now this battle in the denominator of this coefficient, okay? They're growing, and you have this square root happening on there. So, right, I would say, even when you get these parameters, right, I would Desmos it. Desmos that thing. Look at what these values are, where you would plot this value, right, and let's say make this the x variable in your Desmos plot, and then you can see what's happening. And then make epsilon a parameter and just play with it and play with it and see what these values end up looking like. Okay, and what else is this? So we said it's for less, right? We already made the laminar statement, so we already make them know that's consistent, right? But also, this is always also only true if I'm only looking at time around here. On 1 second. Right? So this is not it's not governed by this equation if I'm trying to model that oscillation for like time ticking away at minutes or time ticking away at hours. It's modeled doing that for seconds. So keeping in time what time scale you're looking at and then what h you picked is important for these types of analysis. Right? And then the best thing about this, this very abstract non-dimensional thing, let's just call it B again. Right, is this just has a solution that you can just, right, it is a great solution, right? And even if it didn't have a solution you can look up, you could actually like at least attack it better through series, right? You could say, well, beta is going to be really, really small. You could do a series approximation, some asymptotic methods. We'll all learn about them. They're going to be awesome. But you have a better, much better, well-formed problem to attack for your fluid. And then you just redimensionalize later. So again, look at this. We'll just like just look up the solution, right? I'm okay with it. You plug that thing into D-solve on Mathematica. I don't care. You're remote. It's up to you. Okay, that's the general solution based on B that you can get. You can do the integrating yourself. Hopefully, went through ODEs, and you could do it yourself if you wanted to. It's it's a lot of steps. So general solution, right? You have the B, which is a parameter, and then general solutions come with coefficients or integration factors, right? The way you calculate these, right? You get, just reminding you. The way you get them is from applying your ICs, because you know this function at 2 different values, right? You say, well, I know that this is h, so you set this equal to that, and then you know you set this equal to that, or you evaluate it at 0. Excuse me. OK. So I would say, actually, do this. Figure out how to do this in Mathematica, setting up 2 equations. So you would need to use the solve function, and it's just 2 systems of equations. So you would have to define this, and then solve a system of equations, and then ask it for A1 and A2. And figure out how to do that. If you can do that week 1, you'll be way faster at almost every part of this class. So I'm not assigning it, but go ahead and try it. Or type this into Wolfram Mathematica, look up the documentation on the solve function, and say, give me my A1s immediately. It's real quick. So if you do that, then now you can even say what A1, A2 are. -1. Okay, and that would be that, right? And that's it. And then again, you can do more with this actual solution, right? Let's call this a frequency. And that's another good form of analysis, right? Because now, right, now if you then just define that as the frequency, you have a prettier solution, right? Now, I mean, really, I have 2 over, yes, so now this is b over 2, the frequency cosine, okay? Frequency, and then negative out front. Right? That's great. Now you have analysis on frequency. Now you have analysis on that parameter that we calculated right here. And now you've totally characterized the oscillation of fluid in the U-tube. Amazing. I think it's super. I like that example. My advisor showed me that example. I think it goes over so many different steps. There's no Navier-Stokes equations yet for doing like a more specific, what are the forces happening right now? But really that process, I think, of doing like, what time am I looking for? What H is going to look like? Doing scale, substituting into the differential equation. It's really all there. And you can go further on this too, because then you can go like, well, what if I didn't know this? And you can do an asymptotic approach on it as well, which helps you learn it. But I stop here just because I think it does enough of showing you what type of analysis you can do right here. I have a 1 over omega here, right? I can calculate this omega. So again, I mean, plot this solution, right? Use Desmos again. Desmos it, plot it. Make b and omega parameters and see what it looks like. There's oscillations, right? Does it decay out really quickly? Do the whole same process, right? Do the entire process again, but do it with a different time scale and look at that differential equation. These are things you can now do in a non-dimensional world. We didn't even redimensionalize it too, but like we can do that again as well. So that's what you have to look forward to in this class. So hope you're excited, I think, about the techniques we'll learn and just kind of how you can go from math and make statements about viscous forces. What time scale am I looking for? Clearly, these forces don't match. You hopefully would gain that intuition. It seemed the way maybe it's too, maybe you're like, whoa, slow down there, cowboy. I have no idea what viscous or things like that. If you don't know what viscosity it is, you should not be in this class. But hopefully that has wet your whistle and made you excited for like things you can do in this class when you're done with it. You even do way cooler, more advanced things. But up next, we're going to start on the Navier-Stokes equation. So this is kind of just an intro thing. So next, we're going to start the whole class. We're going to begin like, what are those Navier-Stokes equations exactly? How do they come around? What are they? And then it'll take 2 lectures to really get them. And then once we have them, we're kind of just going to throw it away and just start solving problems again. But I think it's important that everybody goes through it at least once. All right. Thanks. My name's Sam.